up the coursework was coming up for submission. But what were we engaged with? We had started the chapter on the Laplace transform. So we're going to continue with that. Just very brief, just extremely brief recap. We're studying the Laplace transform as a method for finding exact solutions to certain classes of differential equations. Okay, so at the start of chapter 2, it goes through a bit of the classification, or just a bit of the terminology associated to differential equations, and we'll be solving, when we get to it, probably next week, we'll be starting to solve differential equations of this form here in equation 2.1 there, that shows a general linear ordinary differential equation. So it's ordinary differential equation. So the unknown function y is just a function of the single variable t, not a multivariable function. So it's just ordinary derivatives. You've got derivatives of different order, but they're never multiplied together, and the derivatives are never raised to a power. So the differential operator applied to y is a linear one. It's a combination of derivatives of different orders. And those derivatives are multiplied by coefficients. So it's termed a constant coefficient, ODE. So these coefficients of the various derivatives of y are all constants. But then we do have a non-constant term. So the term in the equation which isn't the term in the equation which doesn't have a factor of y in it or any derivative of y, that g of t sitting there on the right-hand side, that's allowed to be a non-constant term. That can itself be a function of the variable t as well. So these are the kind of things which we're going to be able to solve using the Laplace transform method for reasonable choices of the function g. Now, we introduced last time this object called the Laplace transform. It's a transform. It's an operation which you perform on functions. Functions defined by, using the variable t. So ultimately what we're going to do is we're going to transform the whole differential equation, convert it into an equation of a different kind, and then solve that other equation, and then do an inverse transform to bring the solutions back to the solutions of the original ODE. So the thing that does this transformation is this object called the Laplace transform. And it takes as its argument a function f, function of the variable t, and when it gives you back a function, a new function of a new variable s. And it's defined as an integral. So you integrate from 0 to infinity with respect to t, and you integrate the product e to the minus st times f of t. So you're integrating out t. So the Laplace transform has no dependence on t, because you're summing up all the values of the integrand there across all values of t from 0 to infinity. So the dependence on t is lost, and what's introduced is a dependence on this new variable s. So this transform goes by various notations used to refer to it. On this line here, 2.5, these are all different types of notation that are commonly used to refer to that. The most descriptive one is the curly L standing for plus, and that makes it look nice. It's curly L is an operator that acts on the function little f of t. That's that's kind of my preferred notation for it. So curly L reminds you it's the plus, and it's acting on the function f. Okay. But these other types of notation, well, if the argument function is called little f, then we can also denote the Laplace transform. There's a few different conventions. One convention would be to put an overline over the old function name to indicate that it's not the old function f, but it's a new associated function. So you could have f bar of s, that could refer to the Laplace transform. Or another convention that's often used is you have lowercase letters for the original functions defined on t, and their uppercase versions for the Laplace transform. So capital F of s could refer, or could denote the Laplace transform of the function little f of t. So you just have to be alive to the fact that, you know, there's no unique piece of notation that's used everywhere for it. Different sources that you look at, and different places in my notes, and different books that you encounter, you'll see various notations used for the Laplace transform. But they're all referring to this integral transformation of the function f here, transform of the function f. So this is going to be our main tool, our main device in solving the differential equations. So what we first need to do is build up some knowledge about the properties of this transformation. Okay, so that's what's coming for the rest of this session this morning. And just to say, over the page, when you go over the page there, we've proved a few of these, but there's an extract here from the formula book which you'll have in the examinations. This has a couple of pages on Laplace transforms. And here, this is what we refer to as the table of Laplace transforms. So down the left-hand side, we've got a lot of familiar functions, standard functions. And on the right-hand side are their Laplace transforms. So this, on the right-hand side, is the result of that integral. Integral of e to the minus st times f of t, where f is these various functions here down the left. Okay. So these functions down the left have parameters in them, n or a or omega here, frequency parameter. And so those crop up in the transforms as well, as you'd expect. Some of these we've proved so far, the Laplace transform of the constant function, the Laplace transform of t. We proved those before Christmas, that they were 1 over s and 1 over s squared and so on. Should look back at those. And we'll prove various other ones. Then the rest of the table is summarizing, well, these are some new functions introduced down here, which we'll encounter soon enough. And then the other side of the table is summarizing some important properties of the transform. And some of those that we're going to look at and prove now. Okay, so on the following page, page 44 is where we start to list and describe some of the important properties of the transformation. So I'm going to switch to the visualizer now, and we'll go through the proofs of some of these. Do stop me as I'm going through them at any point. Any point you want clarification on any of these things, do just stop me and ask. Right. Now, so the first property is here in 2.1. Now, we actually went through the proof of this before Christmas, here in 2.1, but it's no harm to just very quickly remind you of it. This is a very nice property of the transformation. A common theme you're studying in detail, like the other half of this unit with Stephen doing all the linear algebra stuff, vector spaces. So we have this important property of linearity. So the transform is linear. That's what here in 2.1 is. What does linear mean in this context? I.e., if you take the Laplace transform of a linear combination of two functions, so if alpha and beta are real numbers, f and g functions, f and g are functions, and we have to assume that they have themselves Laplace transforms, if the Laplace transforms of those functions exist. Well, linearity is, as you would expect it here, L is an operator which you apply to functions, and if you apply it to a linear combination of functions, what we'd like to see is that it's the corresponding linear combination of the individual transforms. This is our first fundamental fact about the Laplace transform. It's a linear operation. Now, what do we consider the proof of that? Well, you see, the Laplace transform is really a certain type of integral. We're just going to make use of the known fact to us, known fundamental property, that integration is itself a linear operation. Okay? So when you take the Laplace transform of alpha f plus beta g, by definition, you're taking a certain integral of this exponential e to the minus st multiplied by alpha f plus beta g evaluated t. dt. This is the integral you're performing according to the definition. Well, here you've got a linear combination of functions, so you can just apply the definition of what that is. So you'll have e to the minus st, you'll have an alpha times that times f of t, plus a beta times e to the minus st times g of t dt. Just expanding out that bracket there. So now we're looking at an integral of this compound function. The compound function we see as a linear combination of this. You've got alpha times this product here, plus beta times that product. Obviously, an integral of a linear combination. So we make use of the fact that integration is linear. See, so the integral of the sum splits up as the sum of the integrals, and those constant coefficients, alpha and beta, they can be brought outside. So that's just there's not anything significant, just rubbing out my mark there. And beta times the second integral. So there I've used, just better justify that, this is by the linearity of integration. And we went through this argument before Christmas, but just having it here. So integration is linear, the transform is built out of integration, the transform inherits that property of linearity. Okay? Because what you're looking at here is exactly alpha times the Laplace transform of f plus beta times the Laplace transform of g. Okay, sometimes we write f of t in there or g of t, but that's just indicating that the parameter or the argument of f, the variable of f, is called t. But you can admit it if it's understood. So from beginning to end there, you have the linearity property. Okay, and the important justification, the reason that the transform is linear is because integration is linear. Okay, any questions about that or clarifications I could provide? So that's where we finish really before Christmas. So we'll move on now through the other properties. And this feature is very important. Because when we take the Laplace transform of the whole differential equation, the whole differential equation is a sum of a load of things, a linear combination of a load of things. So we're going to use that linearity property straight away when we take the transform of the whole equation. We break it up into a linear combination of the various terms that appear in the equation. The next property, theorem 2.2, and this refers to derivatives of the transform. So it's stated there in the, well, it's stated there in the notes in one way, but let's state it a slightly different way. If f of s is the transform of little f of t, then the derivative of f with respect to s, this is the Laplace transform, well, minus the Laplace transform of t times f of t. So we'll talk about an application of this after we proved it, but you can kind of see something about its utility here. It's that if you know the transform of f, then we've got a nice way to get the transform of t times f. We just differentiate the transform of f. That's what it's saying. So there's a nice link between differentiating the transform with respect to its variable, because remember s is the variable of the Laplace transform. That's the same, or that corresponds to multiplying the original function by t. So the new function you get, the derivative of capital F, this is the minus the transform of t times f. So let's look at the proof of that. Well, we'll prove it directly. So df ds is the derivative dds of this Laplace transform. The Laplace transform, by definition, is this integral. The integral, the exponential times f of t dt. That's just true by that's just by definition. Well, now we're going to interchange the order of these operations of integration and differentiation. There are operations with respect to different variables, s and t, with respect to independent variables. So without too much extra assumptions in that, we can interchange their order. So this is the integral from 0 to infinity of, and well, now let's write it as a partial derivative with respect to s, because the thing we're applying it to has a couple of variables. Okay, so that's interchanging the order of those operations. Interchanging the order of differentiation and integration. And that's justified because they're independent variables that those operations are done with respect to. And we might need some other, perhaps we might need some other assumptions there about the well-behaved nature of f, but just assuming we can do this. Assuming this is valid, which it will be for all reasonable choices of f. But now we can actually carry out the differentiation. Now, we have to differentiate with respect to s, this product, e to the minus st f of t. Well, you're differentiating with respect to s. T is a different variable, so this f of t there should just be treated like a simple constant for the purposes of doing this differentiation. Okay, remembering our techniques of partial differentiation. So the f of t just remains there unchanged, and we just differentiate e to the minus st. Differentiating e to the minus st with respect to s gives us minus t e to the minus st. Derivative of the exponential is just the same exponential, but then we require use of the chain rule there because the argument of the exponential isn't just s, it's minus t times x. So get this derivative of the argument of the exponential. Derivative of minus st with respect to s is minus t. And the f of t is still sitting there, multiplying it. T is independent of s, so this is just like a constant multiplying the exponential. And, well, you can see what to do with that. Given the result we're trying to prove, see this minus sign can just come out the front. And then we just reorder the product of factors there and just package up the t times f of t together. So what we're seeing now is the negative of, okay, the integral of this exponential times this function. That's exactly a Laplace transform. The integral of this exponential times a function of t is exactly a Laplace transform. A Laplace transform of what, in particular, of t times f. Okay. So, again, from beginning to end there, we've just proved directly this result that we want. Okay, so first, let's look at some applications of this. Or any questions about the argument? Okay. Yeah, I'll just relook slightly. So let's look at an application of this. we already proved that the Laplace transform of the constant was 1 over s. The Laplace transform of the constant function 1 is 1 over s. Well, that implies then that the Laplace transform of t, you can consider t as just t times the constant function 1. The function f of t equals t. You can think of that as t times the constant function 1. So this should be minus dds of 1 over s. So in other words, minus 1 over s squared. Which indeed it is. If you check back on the table of Laplace transforms, back on page, it's got a 20 on it, because that's its number in the formula handbook. So page 42 of your notes, page 42, see the transform of t. Sorry, I've got these two minus. Sorry, the derivative of 1 over s is minus 1 over s squared. So if you add another minus sign, it becomes plus 1. You see that agrees with the result that's in the table. The Laplace transform of t is indeed 1 over s squared. And by extension, we can apply, using induction really, we can apply this to any power of t. Okay? So that's going to imply that the Laplace transform of t squared, well, it's going to be minus dds of 1 over s squared, and that's going to be minus 2 over s cubed. So 2 over s cubed. If you keep going by induction, using induction over the exponent, you see the exponent here, we're going t to the power 0, t to the power 1, t to the power 2. Just using induction over those exponents, you can prove that when you take the Laplace transform of t to some power n, well, it's the same as differentiating n times the result 1 over s. Okay? Each time you get the positive version, 1 over s to the power n plus 1. So when it's t is 0, you get s to the 1. When t is 1, you get s squared. When t is squared, you get s cubed. And you're going to start to pick up factors up here. When you did t squared, you get a factor 2. When you do t cubed, you're going to get a factor 3 from differentiating the s cubed, and that's going to multiply by the 2, which is already there. So what's it going to look like? It's going to look like n minus 1 factorial over s to the n plus 1. Sorry, not n minus, no, n factorial, excuse me. Off by 1. So n is the power on the t. So if t is 0, you have 0 factorial, which is 1. T is 1, you have 1 factorial, which is 1. T is 2, you have 2 factorial, which is 2. Then you'll get the extra factors multiplied on each time. You get n factorial over s to the power n plus 1, which agrees with the result in the table. Look back to page 40, got that exact result. So that's so now we know what the Laplace transform of all the powers of t are. N factorial over s to the n plus 1. Another example is to consider what the Laplace transform of t times cosine of omega t is. Now that's an entry on the table, kind of halfway down the table, t times the cosine of omega t. Well, we can apply this theorem we've just proved by saying that this should be minus dds of the Laplace transform of cosine on its own of omega t. That's omega, the Greek letter omega, just often sometimes used for frequency terms, as it is there, it's multiplying the argument of cosine. So if we take this result, so we'll go to the table. It's an exercise you can do using integration by parts to derive it straight from the definition, but we'll just take it off the table for now. Looking at the table, the Laplace transform of cosine omega t is s over s squared plus omega squared. This should be minus dds of s over s squared plus omega squared. Okay, well that's s over s squared plus omega squared. You can use the quotient rule to differentiate that. The denominator is going to be s squared plus omega squared over squared. And the u's, you can have s squared plus omega squared minus u dv, and the derivative of the denominator with respect to s is going to be 2 times s. So it would seem to be minus s squared plus omega squared over squared, minus s squared plus omega squared. So this minus sign at the front is going to turn into s squared minus omega squared over s squared plus omega squared over squared. Which hopefully, if I haven't made any mistakes, should agree with what's halfway down the table, page 40. If it does. Which is the transform on the table. As expected. So this is a property about how differentiating the Laplace transform, and that relates to multiplying the original function by t. There's a little exercise here. See example 2.5 at the bottom of page. So this thing with the powers of t, this was example 2.4 from the notes. And now we can move on to example 2.5. Which is really just combining the linearity property with that property about transforms of powers of the variables. So there, what we'd like to say is, what is the transform of a polynomial? Well, my notation. Sorry, there's a couple of misprints there at the bottom of page 44, just in my indexing and variables there. But we're trying to say what the transform of a polynomial in T. See. So that thing in the curly brackets there could be a general polynomial in T. Adding up coefficient times the power of T, or powers of the index, values of the index from 0 up to some value n. So this would be a general polynomial of degree n. Well, we can do this, we can say straight away now what the transform of that is going to be, what the Laplace transform of that is, by combining the results we've just done. So the thing we see on the outside operation on the polynomial there is a linear combination. It's a summation operator, a linear combination. We've got these alpha i's, assuming take it that the alpha i's are real numbers, real coefficients. That's a linear combination of functions of t. So just use the linearity property, first of all. Now you've got the Laplace transform of t to the power I. So we say the Laplace transform of the linear combination is the linear combination of the individual Laplace transforms. So this is using linearity. Theorem 2.1. Now we can use example 2.4 about what these individual Laplace transforms are. So we have I factorial over s to the power I plus 1. So you get this linear combination of powers of reciprocals of s as the Laplace transform of the general polynomial in T. So that's the final thing there is using example 2.4, Laplace transform of t to the power I equals whatever. Okay, any queries based on that? Now the next property is the really crucial, well, I mean, they're all really crucial because they all play a role, but the next property is the one that's particularly obviously relevant to dealing with differential equations. Okay? This is theorem 2.3, and this is about the Laplace transform of a derivative. And this is really the property that makes the whole thing click. So I'll use the same notation here. So I'll use the notation that's used there in the book. So f of t is a function with a Laplace transform, so that integral converges, that integral exists with the Laplace transform. Then, so this is the key result. What is the Laplace transform of the derivative of x with respect to t? Because your differential equation, of course, is made up of loads of different, few different derivatives of the unknown function. So as long as we assume that x has a transform, this property tells us what the Laplace transform of the derivative of x is going to look like. And it's very closely related to the derivative of x on its own. Okay. So it's very closely and very well related to the transform of x. It's simply s times the transform of x minus the initial value of x. And you can kind of get the idea of how the whole process is going to work. When you take the Laplace transform of a whole differential equation, see, on the left-hand side of the differential equation, you've got a linear combination of different derivatives of x, of the unknown function. So when you take the Laplace transform of that, using linearity, it breaks up into the linear combination of the individual Laplace transforms of the different derivatives of x. But this property shows you, and by extension, by iterating it with itself to higher derivatives, shows you that the derivative of the transform of the derivative is very well and very clearly related to the transform of the original function. So you don't get, when you take the transforms of the different derivatives, you don't get a bunch of different functions. You just get a bunch of multiples of the one function. Transform of your unknown function x. It's going to be multiplied by various powers of x. Okay, but then we'll be able to treat them all together. But we'll see that happening. Next week. For now, we'd like to prove this, and we prove it directly. Just we start off the left-hand side, and we'll work our way to the right-hand side. Okay. So it's a direct proof. So we want to take the Laplace transform of the derivative. Now, what tools are we going to use in our proof? Well, the transform is defined using integration. So we're going to have to use certain properties of integration. So we're integrating from 0 to infinity e to the minus st times the derivative dx dt. Now, we don't know what x is. X is just some general function. So we're looking at that integration. We're looking at that integral. Now that integral is screaming out at you what it wants you to do to it. Yeah? If you see an integral presented like that, an integral of some kind of familiar function, an exponential, multiplied by the derivative of something, that is kind of shouting out to integrate me by parts. Okay, because it's set up in readiness for integration by parts, because you see it as an integral of a product of two things. One of the things is fairly familiar and standard, an exponential. The other one is expressed as a derivative of something. So we should use integration by parts. How do you integrate that by parts? Well, you take the product of these two things, e to the minus st times x of t, evaluated at 0 and infinity. And then you subtract the integral. Now you swap you take the derivative of the other fraction. So we do ddt of the exponential e to the minus st, and we have x of t left alone, undifferentiated. So that's integration by parts. Dealing with the unknown function x, but you see in the original integral it's the derivative of x. So you can just apply the integration by parts property. Now what happens up here? Well, you see we're assuming that x has a Laplace transform. So that means, as we discussed before Christmas, it means that the function x has this property that it's going to be eventually dominated by the behavior of the exponential. See, this exponential, e to the minus st, that's going to converge to 0 quite fast, as long as the real part of s is bigger than 0. Assume it is in this. As t goes to infinity, this is 1 over e to the st. So the e to the st on the bottom, or real part of s bigger than 0, that's going to grow in size very quickly. So the fraction 1 over it is going to decrease. So at the upper limit, you get 0. At the lower limit, you get, these are limits for t, so you get e to the 0, which is just 1, times x of 0. So that's where the minus the initial value of x comes in. And what do we have here? Well, here we have minus, well, we have to differentiate e to the minus st. When you differentiate e to the minus st, of course, you get differentiated with respect to t, you get s times e to the minus st, well, you get minus s. Differentiating the exponential, e to the minus st with respect to t, you get minus s times e to the minus st. So you can see how this is going to tidy up. We've got minus x of 0 here. We've got two minus signs. We've got a plus sign. And the s now, well, you see, this integral is an integral with respect to t. S is an entirely different variable to t. So as far as the integral is concerned, this s is just like a little constant symbol. as far as the integral can see. The integral is changing t. But s doesn't change when you change t. So this s can move outside the integral. And inside we're left with e to the minus st x of t dt. But of course, what is this? What is this integral? Integral of an exponential times x. That's the Laplace transform of x by definition. This is s times the Laplace transform of x. So as I said, it's a direct proof, just straight from the left-hand side to the right-hand side. S times the Laplace transform of x minus the initial value. And that's kind of the importance of that for dealing with differential equations. The importance of that should be clear because it's relating how the transform of the derivative is with respect to the transform of the original function x. Okay? So you have a constant difference, which is the initial value of x, and it gets multiplied by x. So it is a different thing to the transform of x, but it's nicely and pretty clearly related to the transform. Okay, you can see in the notes on page 45 there's a corollary to that which generalizes it, extends it to derivatives of any order. So you can have a think about how you prove that using just this initial case, and then it's really just iterating this result. Say the Laplace transform of the second order derivative is just the Laplace transform of the derivative of the first order. So have a think about how you generalize this to the corollary, and we'll pick this up. We'll pick this up next week. Okay, so next week we'll deal with continue this with the corollary. And then just for this week's tutorials, and in the meantime, give you some further work to do across the weekend into next week, be looking at exercises 2.1, page 47. Okay? Lots of exercises there with the definition of the transform, and working with the table of the cost transform. Exercise 2.1.